These ancient rocks are 4.5 billion-year-old time capsules, drifting through the dark vacuum of space since the solar system first formed. Identifying how life began on Earth requires capturing the chemical secrets trapped inside these pristine, untouched materials. That goal drove NASA to launch the OSIRIS-REx spacecraft, beginning a 7-year, billion-dollar journey into the deep dark. Mapping our own biological origins back to the stars means firing a highly engineered, multi-million-dollar bullet across the solar system to catch a tiny speck of ancient dust. Before the spacecraft ever left the launch pad, scientists had to pick a single target out of more than 500,000 known near-Earth asteroids. They narrowed them down based on strict physics. They needed a carbon-rich object, orbiting near Earth, large enough to study. One more variable: rotation. Fast spinners fling loose dust into space. They needed a slow spinner, leaving exactly one candidate. The winner was Bennu. At 492 meters wide, it is slightly larger than the Empire State Building. But Bennu's size creates a significant hazard. Its gravitational pull is so weak it measures just 1/100,000th of the gravity you feel on Earth. Bennu was the ideal scientific target, but its microscopic gravity created an environment where any physical miscalculation during the approach could cause the spacecraft to drift away or crash. After cruising through space for over a year, the spacecraft finally arrived to find a landscape far more hostile than expected. Instead of sandy expanses, Bennu's surface was choked with jagged, massive boulders. Earlier thermal mapping from Earth had suggested the surface would behave like a desert, heating and cooling in ways that indicated fine-grained sand. Those readings were wrong. The team had to pivot. For 2 years, OSIRIS-REx hovered just 1 kilometer above the asteroid, mapping every meter of the terrain to find even a single patch of clear ground. They finally pinpointed a site named Nightingale. It was a tight squeeze, a clear patch the size of a small parking lot, directly flanked by a rock the height of a 2-story building. Reaching the asteroid was the first victory, but the mission now required the spacecraft to thread a needle in deep space to touch the only viable patch of dirt. To collect the sample, engineers utilized a robotic arm known as TAGSAM, the touch-and-go sample acquisition mechanism. Direct contact is dangerous. Because the gravity is so weak, the surface rocks are barely clinging to each other. If the arm applies too much force, the entire spacecraft could sink into the asteroid, sinking as if you stepped into a pit of plastic balls. To stay safe, TAGSAM uses a workaround. The moment the arm makes contact, it fires a high-pressure blast of nitrogen gas. This agitates the rocks and blows them upward into a collection chamber. Immediately after the gas fires, the spacecraft ignites its thrusters to reverse course, pulling away before the asteroid can swallow it. This operation was never a landing. It was a timed heist, using gas dynamics to snatch the payload instead of a physical grip. On October 20, 2020, OSIRIS-REx began its autonomous descent toward the Nightingale crater. When the robotic arm hit the target, the surface offered almost zero resistance. The mechanism plunged 0.5 meter deep into the asteroid's crust. The nitrogen blast fired exactly on cue, triggering a massive eruption of debris that swirled around the spacecraft. OSIRIS-REx immediately fired its engines to escape the cloud, leaving a fresh crater where the arm had struck. Once clear, the probe had to verify its haul. To weigh the invisible sample, the spacecraft spun 360 degrees. By measuring how much energy it took to complete the turn, engineers calculated the exact mass of the newly captured material. Despite a deceptive surface and the lack of gravity, the engineering gamble worked. The cosmic prize was secure. In September 2023, the sample capsule finally returned to Earth, landing in the Utah desert. To see why this mattered, look at the Stardust mission in 2004. That spacecraft traveled for years just to return 1 single milligram of comet dust. OSIRIS-REx returned 121.6 grams, more than double what scientists had hoped for. Analysis of these rocks revealed the presence of water, amino acids, and uracil. Finding these molecules in a pristine extraterrestrial sample reinforces the theory that the components for life arrived on Earth via impacts from space. 70% of this material is being locked away for future generations of scientists who will use laboratory technology we haven't invented yet. A tiny fraction was shared with museums, including the Smithsonian, so the public could see the material that formed our solar system. This mission also serves a practical purpose. Bennu often crosses Earth's orbit, and there is a small chance it will collide with our planet in the year 2182. If we ever need to deflect Bennu, understanding its physical structure is the first step in designing a defense system. OSIRIS is already moving on to its next target. It fired its thrusters and is now en route to intercept another dangerous asteroid, Apophis. By reaching into the deep past to find our origins, the OSIRIS-REx mission has provided the engineering blueprint needed to protect our future.